Thanks for the introduction. I'm Davide Andrea, a PhD student from University of Messina, and today I'll present a work carried out in collaboration with the ST Microelectronics site in Catania. I'll start my presentation by introducing the subject of this work, which are direct bonded copper substrates, which are specialized materials aided to ensure thermal management and electrical conduction in power electronics application. They consist in copper layers bonded together with ceramic layers with the dimension in the order of micrometers in thickness, in which and the ceramic layer can be made in aluminum oxide, aluminum nitride, and silicium nitride. The problem in these components is that they usually fail for by delamination when thermal cyclic loaded, and it was observed that this problem can be mitigated by dimple insertion, which consists in subtracting material in the copper layer. Before talking about the methodology proposed to ST Microelectronics, we have to focus on what was made before, and we started our analysis by searching for works applying fractal mechanics in these components, and we found the work by Geyser, in which an experimentally measured crack in the alumina was modeled by finite element method and simulated to understand how it propagates in the ceramic layer. And in this work, the copper contribution to the failure is treated like as an external load. So we also find a work by Klusak in which they treated the interface of between materials like a welded joint, and by doing so, they applied the said strain energy density methodology to investigate the critical area around the notch. So we proposed this methodology to ST Microelectronics and used two different approaches. But the first step was to create a parametric model. For clarity, is reported the cutting plane of the area of interest, and the area of interest is highlighted in green. And we investigated the dimple position and dimension together with the notch angle, opening angle by making them varying with two different approaches. We used the full factorial approach to investigate dimple position together with the notch opening angle. And after that, after understanding how it behaves, we used a statistic approach by creating a dataset by Latin hypercubic sampling. And it allowed us to investigate also the third variable together with the other two. So we investigated also the dimple radius. A very fine mesh was created in the neighborhood of the notch, and we used the unit system coherent with the micrometer because they are very small components. And in the table are reported the material properties, which are the cause of this problem, in particular, the difference in thermal expansion coefficient. Okay. We simulated the holding phase of the real FADIC experiment they made, producer made on these components. So we focused our attention on the maximum temperature, which is 150 degrees, and the minimum temperature at minus 40 degrees. And obviously, we used the X symmetry condition and used the fixed constraint on the left side to simulate the presence of the rest of the components. So to give to simulate, yes, the presence of other material. Before talking about strain energy density result, we have to focus our attention on the phenomena in the around of in the neighborhood of the notch, and it can be observed how at maximum temperature copper expands way more than alumina and cause a compression state on the ceramic layer, while at minimum temperature it can be observed how copper contracts more and apply a tension state. So it's the thermal fatigue test became a mechanical fatigue test. Here I reported said result for several configurations in which dimples are inserted at different distance from the notch, and it can be observed how also the no dimple configuration in black. But the interesting part is the graph on the right, in which can be observed the different percentage difference between every configuration in dimple positioning with respect with the no dimple configuration. And it can be observed how for angle approaching the 90 degree, the dimple insertion is way more important than what happened for angle approaching the 135 degrees. And another interesting thing is that the same energy level can be reached in different configurations. So by doing so, we gave designers a methodology, a logic to positioning dimples and to understand if they are essential to the correct behavior of the component. After this analysis was performed with a full factorial approach, we tried to obtain another point of view by statistic concepts. And the first step was a correlation analysis in which we investigated how each input variable influenced the output, which was set to be the ratio between the Z calculated for each configuration and the worst possible configuration, which resulted to be the no dimple configuration with an opening angle of 90 degrees. On the graph on the left, we can see that a correlation between the X distance parameter and the dimple radius parameter was detected, but it was obvious because X distance was the sum of dimple radius and another variable which was copper increase, and this affected the machine learning algorithm in the end. So we continued our analysis by talking about the copper increase, which resulted to be direct correlated to the output, while the notch angle magnitude and the dimple radius resulted to be to have an inverse correlation, so affected negatively the output. After that, we used two tree-based learning algorithms, which are random forest and XGBoost, which give to obtain a model on a tree-based algorithm and they work similarly. So the first one work with the parallel trees, which make the decision independently, and in the end merge their choose. While the XGBoost work with sequential trees, and each tree tries to fix the error given by the previous one. These models were trained using the 80% of our data deriving from our simulation, and they were validated by 20%, and in the graph can be observed respectively in blue and red. And their performance was evaluated by by calculating the coefficient of determination and the mean absolute error. And we used the 500 simulation to investigate the whole domain of variables. Here is reported the response surface obtained by random forest algorithm, and it can be observed two variables influence can be observed at time. Just two variables at time can be observed, while the third one affect it like a ghost variable and can be not observed directly in the graph. And it can be similar surfaces were obtained by XGBoost algorithm, but it can be noted that it was most affected by noise and in the distribution of data. And in the end, to understand how algorithm worked, we did a shape analysis, which allows us to understand how the algorithm made the decision. And it can also be observed how for example, by analyzing the random forest one, high values of notch angle affects affects output by decreasing it, so the shape values are negative, while low values of notch angle affect them positively, increasing that the output, the objective function, with respect with its mean values. The same is for the dimple radius, and as we said before, for the inverse correlation of copper increase to the output, we saw the contrary on that. As I said before, XGBoost showed to be more affected by noise, and it can be also observed in this shape analysis, in which blue points in notch angle are in the left side of the graph, so affects negatively the output, which is inconstant with what we observed in the full factorial analysis and before with the correlation matrix. In the end, we obtained the optimal parameters estimated from the model trained on our data, and they resulted to be coherent with what we expected and what ST already knew. And in this case, for this case study, random forest seemed to be more effective on our data distribution, but it is also due to the fact that we investigated just 3 variables together, and maybe XGBoost was too redundant on that. On the right, we can also observe how they both worked similarly, but random forests give more importance to the notch angle variable, while they worked similar on the dimple radius and the copper increase. In conclusion, I'll make a short summary about what was done, and we applied the local approach to investigate different geometrical combination. We investigated the problem both in full factorial, so investigating all the possible combination, and statistic approach. And most importantly, we used an energy parameter, a local approach, to give a global parameter to compare more geometric combination. We also used the machine learning to obtain a different point of view on the problem, and it resulted to be coherent with what was expected. Thanks for the